Hello, everyone, and thanks for viewing my talk today. As the title suggests, I'm going to be talking to you about female bias vision in the Carolina grasshopper. And we're going to be talking about how some recent behavioral data that we've gathered in the lab matches previous data on the eye morphology. Before we begin, I'd like to thank Eric Gilbert, my co-author on this talk, who was essentially a one-man field and lab crew during the 2020 season when we did all of this work. So compound eyes are a really cool organ to study in terms of neuroanatomy because of all the morphological variation that we see between species and between individuals. Some of these are illustrated here, and importantly, this variation in eye structure isn't believed to be random, but as a result of the fact that compound eyes are limited by physics and are especially energetically costly. This leads many people who study vision to think about eyes in terms of matched filters. In other words, the form or the shape of the eye should match the behavioral needs of the animal. Notably, compound eye structure doesn't just vary between species, but also can vary within a species, and such is the case in our study species. Today I'm going to be talking about work that we've done in the Carolina grasshopper. This is a member of the Otopodinae, or the bandwing grasshoppers, which is actually a subfamily of hundreds of species with worldwide distribution. As their name suggests, they're known for those band wings that you can see there. But when we started working with them and we're interested in the coloration, we realized that little work had been done on their actual vision, especially in North American species. In addition to having these cool band wings, these grasshoppers also show a size dimorphism. Females in this case are often larger than biological males, although you do get variation within both females and within males. In general, we end up seeing that females are actually, in some cases, quite a bit larger than their male counterparts. Previously, we've documented that the sexual size dimorphism extends to an eye morphology dimorphism, and this warrants further behavioral examinations. More specifically, compared to males, female Carolina grasshoppers have around 15% larger eyes, depending on what axis you're looking at, around 20% more ommatidia, which are the optical units of spatial vision within the compound eye, around 25% finer ommatidial angles, meaning their receptors are more densely packed, and so they should have finer vision, as well as around a 10% increase in predicted sensitivity. However, note that all these are just morphological variation that we've looked at here previously. This begs the question, do these morphological differences match behavioral performance, or are they just an artifact of overall increased size in females within this species? Now, this could extend to all sorts of different behavioral contexts, but the one that we looked at here that actually ended up working out quite well for us is basically a predator avoidance setup. So we ended up setting up a mock predator avoidance trial. Excuse me. And in this trial, we took grasshoppers from the field and put them in a terrarium within the lab. And we were able to track their movement from an overhead camera, which you're actually seeing a kind of distorted shot of right here. We'd wait till the grasshopper was moving towards a calibrated gaming monitor, at which point we just show them a stimulus, which was a growing shape over 7.6 seconds. While we're tracking this and growing this shape, we also have a small number on the corner of the monitor that we're able to read from another camera that tells us the size of that shape. This second camera allowed us to record the response of the grasshopper to that shape, as well as record the exact size of the shape. So by using this system, we can display all sorts of different stimuli to grasshoppers and see if they freeze in response to these looming stimuli, and also at what size these stimuli are if they do freeze to them. Over the 2020 field season, we ran this for 64 different grasshoppers, and we did each grasshopper for 5 different stimuli, leading to 320 total responses. To show you that this method works, grasshoppers reliably freeze, and this is regardless of sex. Here we're seeing that at around 85 to 90% of the time they'll freeze when we have a growing circle as a living stimulus that we show to them. Conversely, if we have a control, they're only going to freeze around 15 to 20% of the time, which is what grasshoppers do. They often stop moving. If we do an intensity treatment to make sure it's the shape that's making them freeze rather than just differences in intensity from that circle, we can see that it's at actually the same level as the control. So they're freezing in response to the shape. Because we're tracking the grasshoppers, we know exactly the stimuli angular size when they froze, based on how far away they were and what that stimuli was, or size that was. And we can see that on average, they're freezing to stuff around 10 degrees, while there is a lot of variability that we see here. So let's get into our hypothesis, though. Are females less likely to miss a stimuli, or in other words, are they more likely to freeze? And if so, are they able to freeze to smaller stimuli than their male counterparts? So it turns out over those 5 stimuli that we presented to them, which were actually designed to test some other morphological variations in the eye that I can't get into today, we found that 3 of those stimuli consistently invoked a response, while 2 of them didn't. Across all trials, female grasshoppers were more likely to freeze for the invoking stimuli, but not for the controller intensity stimuli. So yes, it looks like females are less likely to miss the stimuli. Now there is some pseudo-replication in here. So if you use GLMs that are also controlling for subject within this, all of the most parsimonious GLMs all included terms for biological sex, with females outperforming males. So females are more likely to freeze, and they may do so to smaller stimuli. Here we're seeing the natural log of the stimuli angular size that invoke to freeze, and these are just grasshoppers that themselves froze, not the ones that didn't, because there's no data for that. And while the means and the medians are different, we have an interesting thing of what's going on down here. In fact, we had, out of all the responses that we had down there, the 12 responses to the smallest stimuli throughout all of our trials were all from female grasshoppers, and most of these were from different female grasshoppers as well. Now, we're looking into this field season by presenting smaller stimuli to these and seeing if we can get a more extreme response difference than what we saw with the larger stimuli that we started off with in this particular experiment. Another way to look at this is if we look at the stimuli size by biological sex, and so percentile, and these again are just the ones that froze, we see the 12 responses there, which if you're just flipping a coin, you wouldn't expect. However, some more advanced stats, and I'm still looking into some order rank stats to see if we can parse this out a little bit more, suggest that there may be no differences here. So I'm not quite sure, and that's part of the reason we're running more experiments this summer looking at this. Regardless, though, about the size, we do see that females are more likely to freeze, which means that the take-home message from this whole talk is that the female-biased eye morphology correlates with increased ability to freeze in response to mock predators. And at that point, I again want to thank Eric, who did so much of this work, and I'm happy to take any questions.